Buenos días a todos. Muchas gracias por venir. En primer lugar, obviamente, muchas gracias al doctor Fabián Rosales-Ortega por digamos, hacernos esta visita y contarnos sus más recientes avances en la investigación que está realizando últimamente. Fabián estudió, si no me equivoco mal, la tesis doctoral con Robert Kennicott en la Universidad de Cambridge.
Correcto.
Después yo creo que ya fuiste directamente a la INAOE, estuviste un tiempo en Autónoma, ¿verdad?
No, estuve primero en el CSIC, Santiago Rivas,
vale.
Luego en Calar Alto y luego en la Autónoma de México en Ángeles.
Y luego ya te fuiste a México
y luego ya me
como investigador de la INAOE.
Desde 2012.
No me ha dado tiempo a hacer
no te preocupes.
todo digamos, la investigación que debía haber hecho, lo siento. Y bueno, pues nada, ella lleva ya 10 años.
12 años.
11 años.
12 años.
Pues o sea que ya es un investigador asentado, completamente senior, aunque no tenga tantas ganas como yo. Afortunadamente para él. Pero bueno, pues nada, hoy nos va a contar un poco de a new generation of empirical metallicity relations for the local and high-redshift universe derived from the science, the largest catalog of high-quality electron temperature-based data. So, is there anyone in the online that will prefer the talk to be given in English? Please just raise your hand in Zoom and we'll switch to English, that's no problem. But if everyone is okay, is happy with Spanish, we can proceed with Spanish. So oh, okay. Oh, yeah. So we have someone.
So we have someone.
That's Spanish. That's
no
okay.
Problem.
Nobody's perfect. Usually say. Okay, so you don't mind?
No, that's okay. It's the perfect excuse. So
thank you very much.
No, thank you to you because I just met Armando a couple of weeks ago.
Yeah,
in Mexico, and I just crossed by the corridor and I asked him, "Can I give a talk at the Complutense?" He told me, "Yes, sure." So here I am. Okay, so let's start with this short talk about calibrations, as they are mostly known. So let's start our journey at the Big Bang nucleosynthesis. So we know that at the beginning there was only protons and electrons, and in the first 3 minutes of the universe, by several physical processes, they become hydrogen was formed, the proton, because it was still very hot, but the nuclei of helium, deuterium, and lithium and beryllium were the main components of the universe for a long time. So after the first 3 minutes, and some time have to pass, have to evolve. So after some 100 to 100 million years, supposedly we have the first generation of population 3 stars, which are very different to our the stars that we now know and observe, because they are supposed to be very large and only formed of hydrogen and helium, and very short-lived. But they are the reason of the producers of the first elements, of the first high elements in the universe. All heavier elements are born inside stars. So they are the product of stellar nucleosynthesis and explosive events in different sort of processes. For example, for low mass stars, below 1.3 solar masses, we have as a main component the proton-proton change, the fusion of helium that becomes, hydrogen that becomes helium, and in stars that are a bit larger, a bit heavier, the CNO cycle is the main driver for the production of heavy elements. But we have many other sort of forms of ways to form or create other elements. So the first one are created in the Big Bang. Then we have the main element like carbon, nitrogen, oxygen forged inside exploding stars, supernova. But also we have elements formed by the capture of neutrons. And we have at the end the whole periodic table. And depending on the element that you are looking at, they come from the Big Bang fusion, called the emerging neutron stars, exploding massive stars, dying low mass stars, and exploding white dwarfs. And this is a nicer way to see this table by Teiji Kobayashi. So as you can see, there are like some shades in each of the elements. So time goes this way, and the relative abundance of the sun goes in the other axis. So you can see the oxygen is the large one here, but depending on the element, some of them are produced by AGB stars, by core collapse supernovae, and other by other exotic processes in the universe. And this is very important because depending on the element that you're looking at, the time scales of the production are different. So for the alpha elements, for example, oxygen, neon, magnesium, they are produced obviously by core collapse supernovae with masses, with progenitors larger than 8 solar masses, and they are the shortest in time scale, that you can see here. Carbon and nitrogen are most formerly in intermediate mass stars between 2 and 8 solar masses, and also created in the wings of all-radiate, well, not produced but expelled in the form of all-radiate wings of asymptotic giant branch stars. And then the iron peak elements like iron, nickel, and nickel are mainly by supernovae type 1a, but they have a delay of some 40 megayears to a few megayears. So this difference in the way that, for example, alpha elements are iron peak elements form for a given, let's say, a burst of star formation, the delay time encodes some different star formation histories. And this is important when we study star formation. So the physics of element production is very rich. We have a lot of processes that go from remote nucleosynthesis, the different type of processes inside the stars, helium burning, core collapse, stellar evolution, asymptotic giant branch, many types of elements. But at this point, I've said elements and not metals. Why? Because in astrophysics, term metals refers to all the elements heavier than the helium as we know. This graph is the present-day solar system composition, in which helium and hydrogen are not shown. And as you know, the metallicity in astronomical terms refers to the content of metals relative to hydrogen and helium in the universe. So, why metallicity is important for astrophysics? Well, unlike that matter, the chemical evolution traces many things in astrophysics. Traces the baryonic as the radiative and dissipative processes in the universe. It's very complex, as you know, because the baryons undergo a cooling, inflows, outflows, stripping, loss of mass. The metal content also constrains a lot of things. For example, the evolution of in simulations like this one provides tight constraints on how we produce these simulations and how we understand the universe from simulations that are very complex. In a galaxy, we have, for example, in this model, there are many models, but in this case, we have a simple model in which the gas from the intergalactic medium falls into the potential of the galaxy. Some remains in the halo, some falls into the galaxy, and then star formation begins. And then, as star formation proceeds, we have metals and gas put inside long-lived stars. But some of them return because of the supernovae. This returns to the variable gaseous cycle of the galaxy. Some of them go out of the galaxy in the form of winds, and some of them go out in some even outside the potential of the galaxy. So this is one of many models that have been thought or devised to see how things proceed. But the main point is that metallicity is a direct tracer of the baryonic cycle. That means how the gas falls into the galaxy, forms stars, and returns to the interstellar and intergalactic medium. And we have many processes here: feedback, outflows, inflows, stripping, and many other things that a lot of physics that is going on in these processes. Here you can see just one spiral galaxy in the middle of these processes, but we have recycling glass, diffuse gas, accreting gas in scales that goes from kiloparsecs to even megaparsecs in the universe. So I hope I convinced you that metallicity is very important element that we have to measure and to understand in the universe. But when I speak about metallicity, probably people think about different things in the audience, because, for example, people who are working with the stars are thinking about this concept. People are also working in the stars or star populations, this concept, and people which work like myself with the gas phase of the metallicity think about this concept. So what is the difference between them? So metallicity is refers as the ratio of the mass of the metal with respect of the mass of the values. In this case, hydrogen. And usually the note is relative to the solar value. That's how we know it. But the relative abundance of two chemical elements, for example, X and Y, are just the difference is expressed in terms of the relative number density difference to the solar value. For example, for hydrogen, we have this value, 12 plus log X over H, where actually this is just the relative number density of the element that we are trying to measure relative to the number of hydrogen elements. And we have this 12 because customary this value was introduced so that any element, even the most rare, has a solar positive value in this scale. And that's why we have this 12 plus log over H. And since oxygen is generally the most abundant element after hydrogen and helium, in the gas phase metallicity, normally we express these values as 12 plus log over H. But it's just simply the number density of the elements. So metallicity, as we have seen in the universe, scales with mass. And this is something that we know, and is something that is somehow well understood, because in terms of chemical enrichment, as time proceeds, the metallicity of a system should increase because we have gas put into stars, these stabilizing elements, and then these elements are expelled to the interstellar medium by several processes. And also in a system, also the mass accretes by merging and mass assembly, so both metallicity and mass should increase with time, and that forms what we know as the mass metallicity relation of galaxies. This very common figure by Tremonti 2004 with known galaxies. But the form and the scatter has many implications, and depends on many other factors. For example, the gas fraction that is inside the edge of the galaxy, the inflows, outflows from the intergalactic interstellar medium, also galactic scale outflows in the form of supernovae, stellar winds, AGNs, star formation efficiency, variable initial mass functions, etc. So this dispersion and this form has a lot of physics inside it. And also by systematics in how we measure this axis and also this axis. So this mass function, mass metallicity relation, has also been studied in terms of as a function of redshift. In this work of Sahib 2014, we have that many high redshift galaxies, and we could explore up to a redshift of 1.5, and we see this evolution that we talked about before, that we have more, the assembly of the galaxies increases with time, and also the metallicity. So this is somehow expected. Now that we have spectra, and we can analyze very high redshift galaxies, we also see a very interesting diversity scatter in how we measure the metallicity and also the mass in the first galaxies of the universe. This is just a publication of this year, which is a compilation of the mass metallicity relation for galaxies up to set redshift 3 and 4, as I remember. Also, another observable of the metallicity is that the metallicity behaves in a different way radially within a galaxy, for example, the spiral galaxy. So the observation shows that in isolated spiral galaxies, we have a steep negative metallicity gradient. So we have more elements in the inner part of the galaxy, and the metallicity decreases with a vector-centric radius. So this is a clue for inside-out or outside-in formation and or quenching. And depending on how the galaxy evolves, we can also have mergings and interaction which could flatten or change the form of this gradient. But when we put a lot of galaxies, not just one, it turns out that we see the metallicity gradient in mostly all of the galaxies, in spiral galaxies. So when we normalize in this axis and also in this axis, the metallicity is quite a remarkable degree. And this gradient also works as a dynamical clock for the interaction that we can have inside the galaxies. But also we can analyze other phenomena like galactic fountains, stellar migration, radial inflow, etc. So now that I try to convince you that how we measure and how metallicity is important, how we measure in this case gas phase metallicity. Okay, if we have a star-forming region composed by gas with chemical components and massive stars that produce ultraviolet photons, then we have this kind of spectra. And this is a spectra from H2 galaxy, a galaxy with low metallicity. We have very strong emission lines, and this is something important because I'm going to stress this a bit. This is taken with a 2.5 meter telescope. This is a spectra from the long survey. So we have very bright emission lines like H alpha, and also bright lines from oxygen and nitrogen and sulfur spectra in the optical, which are coolers. These lines are actually a way that the nebula cools down in the physics. So when we go to another sort of probability, we can also detect other lines, other very, very, very small lines. So in this inset, you can see this very small line here, oxygen 34363. This was taken with the Calaralto observatory, the 3.5 telescope. And, well, you can see this wide range of strong lines in the optical, but also we can start seeing these small lines. So, how we measure gas phase metallicity? Well, the flux of an emission line depends of its abundance. And the ionic species that we can denote like Nx x plus is, well, sorry, the flux of emission lines is the resultance of the abundance times its emissivity. And the emissivity depends on the temperature and density of the nebula, of the region. And we have two types of emission lines. What we call the collisional excited lines of cells, which are typically bright, but they are exponentially dependent on the temperature. And another sort of line, which are the recombination lines, which are little dependent on the temperature, but they are very, very, very faint, some 10 to the 4 times fainter than the collisional excited lines. So, in order to derive the chemical abundance of a region, we need to derive the density and the temperature. So for the electron density, we use electron density doublets, which are sensitive to the density of the gas. For example, this well-known oxygen 2 doublet in the blue, or the sulfur doublet in the other part of the spectrum. When we also need the temperature, and temperatures can also be measured through what is known as auroral lines. So these lines are coming from quite high quantum levels, which are very sensitive to temperature. For example, we have oxygen 34363, the small line that I showed you previously, the doublet oxygen in the red part of the spectrum, and other lines also in the optical part of the spectrum. So in order to derive directly the temperature, we need to observe these lines. But these lines are very, very weak. So remember that I showed you spectra with lines with 2.5 and 2.5 meter telescopes, where these are auroral lines measured in a very nearby galaxy, only with an 8 meter class telescope. So in order to measure the temperature, we need to observe and derive these lines precisely, not also detect them, but to measure them well. And if we derive the metallicity using these lines, we say that we can derive the metallicity through the direct methods, which is not really direct because many assumptions are into consideration. So this is how in the literature are known. But this method is limited because the lines are very, very faint. So it's like 10 to 100 times fainter than the strong emission lines like H alpha or oxygen 3 in the optical. So for measuring metallicity, so we have, in order to resume everything, basically 3 ways to do it. Using recombination lines, which are the most reliable ones, but they are very, very faint, and they are only observable in very nearby regions, mostly in the Milky Way. Then we have the collision excited method that we use these auroral lines with respect to the strong lines to derive metallicity, density and temperature. But the assumptions that we make here is that they are homogeneous regions, that the abundances of the collision excited lines and the hydrogen lines are come from the same region. We also assume local thermodynamic equilibrium and a very simple geometry. And also we can do modeling. So we can construct a model in our computer, but then we have to make many, many assumptions on the ionization continuum, the ionization parameter, the gas density, the structure, and even the dataset distribution. So these are the main, the way to really derive chemical abundances. So what do we do when we don't have these very faint auroral lines? So we need to use something that is called the empirical method of strong line calibrations. But basically we only observe these very strong lines in our spectrum, and somehow we have to derive a metallicity just using these lines. So the way that is done is that we have, for a given sample, we measure precisely the metallicity through the direct methods. And then we compare the metallicity with strong line flux ratios, and then we find a functional form, we calibrate this relation, and then we have an empirical relation. So put it in a plot is that we have this value, that is the metallicity, which is hard to derive because we need the auroral lines, and we have in this axis a strong line index that you can construct somehow, which is easy to observe, relatively easy to observe. And then we have some sort of functional form. This is how we build a strong line relation. And it's a huge industry. So there are many, many calibrations in the literature. They come from the 80s, actually, 90s. And there are many types of how they do it. They can be fully empirical, just using observed samples and then producing this calibration. It could be theoretical ones, using models to reproduce the metallicity and then find the relationship, or some empirical, a combination of both. When we don't have data for a specific region, then we put something from the computer and then we fill the parameter space. So this is an example of how Curtin collaborations did these calibrations using a sample I'm going to mention afterwards. So the problem is that these calibrations have many issues. The bright line estimates of the oxygen can vary as much as 0.4 to 0.8x, which is a lot for the same data. And they have very poorly understood systematics with respect to methods, for example, derived with recombination lines or photoionization models. This is an example of how we compare the mass metallicity relation derived from a particular sample, and how we measure different metallicities depending on the calibrator that we use. And this is also a plot from my PhD thesis, where we measure hundreds of H2 regions in a nearby galaxy, and all of these, the 4 panels are the same data, but 4 different calibrators used that we had at the moment 15 years ago. And you can see this star here was the only region in the whole galaxy where we could actually measure an auroral line. And actually there is an important shift with respect to what we measure from the strong line calibration. I'm going to read it afterwards. So you can see that the shape, the dispersion, the offset is different for each of the calibrations. So this is an issue when we want to measure metallicity. So most gas phase metallicity abundances in the literature are produced or measured using these calibrators. So very few measurements of gas phase metallicities in the literature are using auroral lines. So when you see, for example, this mass metallicity relation, for example, from the slope, the vertical axis was derived using one of these calibrators. And this is a problem. So the critical issues are, of course, the temperature relations, these abundant discrepancies that we saw previously, but also one important thing is the calibration sample. So I'm going to jump into that. So this is an example of a very well-known calibration, a very simple one, which is called the N2 calibration, which is just the ratio of the nitrogen 6584 over H alpha. So the first one comes from Stork and Bergman in 94, and then several other calibrations were proposed, and this in particular is from the Nicolo 2002. And they use a sample of over 200 H2 regions. So for the low metallicity sample, they use the direct method, but they didn't have measurements of high metallicity abundances, so they had to put some models into it. So this is a semi-empirical relations. But well, you can see here that we have this axis, the metallicity, the index, and we have some sort of relation that you can use to, if we observe this value, we can derive some kind of metallicity. In 2004, this is also a very famous calibration. The O3 and 2 was proposed by Max Pettini and Bernard Pagel, mostly because there were two lines. Well, they involve the oxygen 3 and nitrogen 2 lines, which are at that point very good to measure or to be observed, to be found in objects at redshift 2 to 3. So it became very, very popular. And in this case, the sample was even lower than for the N2 calibration, just over 100 H2 regions. And they found this calibration. Again, the squares are models, are not observations, because they didn't have observed lines in this regime. And then time evolved, we observed more regions, and Enrique Pérez Montero and Contini in 2009, they have almost 500 spectra, but you can see the dispersion here. So they are the same calibrations that we saw before, N2 and O3 N2, but okay, we have more regions, but a lot of dispersion. And in this case, we're not talking just about H2 regions. They incorporate H2 regions from the Milky Way and the Magellanic Cloud, but also extragalactic H2 regions and H2 galaxies. So we are starting to put different objects into the same plot, which is also an issue that we had to consider. And this is also a famous calibration. And you can see, well, this is a really nice calibration. You have the oxygen, and this is the N2 calibration. But if you go to the paper, they say, okay, we select H2 regions where the discrepancies in the oxygen and nitrogen abundances are less than a fixed value. And it's everything that they say. So that's why it looks really nice, because everything that they didn't like this, they just throw it away. But anyway, but the point here is that they have over 700 spectra at that point. That was 2012, by the way, a bit more than 10 years ago. And then the way that I entered into this world of calibrations was because a paper by Rafaela Marino, who did her PhD here at the Complutense with Armando, and we used the previous sample from Eugene, and we add more over 184 spectra that we found in the literature. It was a really nice work because we compiled almost all the H2 regions and galaxies that were at that time for a total sample of over 600 spectra. And Rafa produced these really nice calibrations, the N2 and O3 N2 calibration with dispersion and some other problems, but I mean it was an upgrade in this field. But at that point, I had since that time, I wanted to do it in a different way, because as you can see, there's an intrinsic dispersion in all the data. So one thing that I wanted to consider was the quality of the data in all these abundances. Another way to do it is using stacking spectra. So what the group from Curti and Majorino did is that they took a large sample of, for example, the Sloan spectra, and they grouped it in, for example, in a BPT diagram, and they merge and stack spectra of the same characteristics, and they assume that the metallicity should be the same. So they stack thousands of spectra, and they obtain also these calibrations. From that time is that they do start seeing seeing these calibrations in a different way. Like for me, it's upside down. They put in the x-axis the metallicity, and in the y-axis the index, which is a bit odd, but anyway. Okay, but as I told you, the calibration is a huge industry. And now with the James Webb, they observe some galaxies in high redshift, and they produce a calibration for high redshift objects. So these are just papers in the last year, and each one of them is proposing a calibration for high redshift objects using James Webb Spec data, up to 9.5 or 10, 2 to 10 in redshift. So it's something that people are using because they are obviously it's very difficult to observe auroral lines at high redshift, but still now with the James Webb we are able to observe these auroral lines, and people are producing a lot of results on this issue on metallicity. But my point is that the importance of the good results. This is a phrase by this programmer of IBM in the 70s, that if you put garbage in, you're going to get garbage out. So I wanted to focus on how good the sample should be in order to produce good results with calibrations. So the work that I'm going to show you is actually a compilation and a work that I've been doing for the last 10 years. Both of the spectra have been observed in that time, mainly from class 8 to 10 meter telescopes, and now the James Webb. And there was no real homogeneous compilation of data with electron measurements up to date. And the study obviously needs high quality data. So several years ago, I started this compilation of regions. The baseline was the work of Rafaela and Enrique and Pierre Contini, but with the following criteria. They should have at least one optical auroral line from which we could derive the temperature, and one doublet sensitive to the density. But an important fact is that I also include the errors that the people report in the papers. So by 2024, we had a sample of over 1,800 regions, and mainly the work was carried out at that time by a student at INAOE, at the Benemérita Autónoma de Puebla, which is, he was doing his bachelor degree. He is now a PhD student at INAOE, but he did a remarkable work compiling many of this data at the time. But then I met the design group, which are based at the ILC. The PI is Eduardo Méndez Delgado, now at the UNAM, together with César Esteban and Jorge García Rojas, and they were also doing the same thing at the same time. They have a database of over 1,400 regions with the same characteristic. This is a plot of how some of the regions look like, and they call it the Deep Spectrum of Ionized Regions database. And we found out that we have 600 regions in common. So we decided to join efforts and to work together, and we compile now what we call the desired sample, the most extensive literature compilation of auroral line data. We currently have over 3,000 regions, include those of planetary nebulae, in which there are extinction-corrected spectra of ionized regions collected from the literature and also from observations, including H2 regions, planetary nebula, star-forming galaxies, and all of them have the information to derive the density and the temperature using auroral lines, plus the errors, which is something which is very, very important. So using this database, we derive the physical conditions of all the spectra in an homogeneous way using PyNet with updated atomic parameters, and we calculated the oxygen abundances using two conditions. First, the first condition is that, or the first assumption is that we assume an homogeneous temperature, which means this famous T square by the work of Painberg, which means that all the nebula is homogeneous and there are no variations in the density. And also using the relation by Mendes Delgado, which is a Nature paper, considering temperature inhomogeneities, in which this T square is greater than 0, which considers that, which actually solves the problem that I showed you before between this offset of emissions abundance is calculated with the direct method to the recombination lines. So we have actually two measurements of oxygen for each of the regions, and then we apply a selection criteria. So we also restricted the sample to extragalactic H2 region and forming galaxies, local and high-redshift galaxies, now up to 7. But we restricted to regions in which the auroral lines have a relative error less than 40%. The theoretical nebula line ratios, for example, the ratio of oxygen 3, 5007 over 4959 should be 3. The line ratio should be within 20% of error. The electron temperature should be less than 25,000 Kelvin. The error in the derivation of the oxygen less than 0.6x, and the value of the oxygen derived with considering inhomogeneities should be larger or equal than the value considering that the nebula is homogeneous. And from the original sample, we restricted with all these selection criteria to a final sample of over 2,000 regions in total. And with that, we construct new calibrations. So this is the histogram of the publication of the number of regions per publication year. So we have more than 200 publications. You can see from the 2000s, many of these regions were observed. We have some drops here, basically because the COVID pandemic, and also because we didn't have time to put more data here, but I'm going to talk about it later. And okay, it's not probably the completely exhaustive, but as far as we know, we can include all the measurements of auroral lines in this compilation. And we have many auroral lines, mostly 4363, but also regions in which we have multiple lines in which we can derive we can have a very good determination of the temperature using different auroral lines. So this is an example of this N2 calibration that I showed you before. This is all the literature data with auroral lines, and you can also see that we have a lot of errors in the measurements. This is if we plot the calibration without taking into consideration the sample criteria. So I put this example because if we have auroral lines in our spectrum, doesn't mean that it's good quality for the spectrum. That's something that I want to stress, because not because we have auroral lines means that we're going to have a good quality spectrum. So if we apply the selection sample and we clean our sample with the criteria which is common sense, this is what you get. So it's a really nice calibration in which you can have star-forming regions which are basically in the low metallicity regime, H2 regions which are in the middle and high metallicity regime, and some high redshift objects as well. And in that way, we constructed the calibration. This is another example with O3 and 2. This is how it looks if you put all the data without the restrictions. It is how when you clean the data with those basic considerations. And this is how we construct the new calibrations that we are presenting. So this is just an example for the N2, O3N2, and N2O2. In each of the plots, you can see two lines. The one below corresponds to the